I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here. Last night I worked on this paper a little bit while I had insomnia, and I got stuck on a proof, and then when I went back to bed, I quickly realized how to get past being stuck on this proof, and then fell asleep. Near the beginning of the paper, or at the preliminaries part of the paper, the assumption was made that the directed acyclic graph G has the property that no vertex has infinitely many ancestors, and that's the key to get through this proof where I was stuck. I'm trying to prove proposition to be strengthened in theorem, main theorem below. Let us subset G and assume that S satisfies the convexity axiom and S satisfies the IAP axiom and S is not mostly trivial. Then S locally satisfies the Knight-Darwin law. Is this stream working? I'm not seeing it here. Ah, yes, it's working. Okay. Assume the hypotheses. Yeah. So we were constructing a path from W1. Well, let me read the whole proof. Assume the hypotheses. Assume big P equals U1, U2, dot, dot, dot is an arbitrary infinite directed path in S. We must show that some UI has multiple parents in S. Since S is not mostly trivial, S backslash P is not totally trivial. Thus, there exists an infinite directed path Q equals V1, V2, dot, dot, dot in S backslash P. Since V1 has infinitely many descendants in S, namely V2, V3, dot, 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 the IAP axiom guarantees S contains less than infinitely many non-descendants of V1. Right. We need to be more careful. V1 does not necessarily work. What we have to say is, since by the assumption at the beginning of section, prelim section, and I'm of course going to have to go insert that label there. Since by the assumption at the beginning of section, prelim section, U1 has less than infinity many ancestors, there must be some I such that VI is not an ancestor of U1. That's the key. That's the key which lets this all work. Let me say, since VI has infinitely many descendants in S, namely VI plus 1, VI plus 2, etc., the IAP axiom guarantees S contains less than infinite non-descendants of VI. Thus there is some J bigger than 1, such that your J is the descendant of VI. You know what? I don't want to... No, that's okay. I was thinking I could avoid this shifting of variables by discarding part of the V1, V2 in order to assume that V1 is not an ancestor of U1. But I think it's fine. The proof should be easy enough after being fixed in this way. Thus there is some J bigger than 1 such that Uj is the descendant of Vi. This means there is a directed path, a finite directed path, x1 dot dot xn in S, well, not necessarily in S, but with x1 equals Vi and xn equals is there some j bigger than so uj is that a standard of vi? Yeah, xn equals uj. Since S satisfies the convexity axiom, each xi is in S. Yeah. Let K be minimal such that xk equals ul for some L. There exists some such K since xn equals uj. Minimal such that there exists some L such that okay, now note that k bigger than 1 because otherwise the I would be an ancestor of u1, which is contrary to choice of I. That's the key roadblock that was preventing things yesterday. Also, or that should be L bigger than 1. L bigger than 1, because otherwise Vi would be an ancestor of U1. Also, K bigger than 1, since x1 equals Vi is not in P. Thus, UL has two parents, UL minus 1 and X sub K minus 1, which must be distinct because UL minus 1 is in P and X K minus 1 not in P by minimality of K. And that is what was to be shown. QED. Let's commit that. Also, there was this business that, so I had stated lemma, for any S subset G, if S is competition trivial, then S is mostly trivial. And then there was a problem with that, which is that in order to prove that, you would need to use Koenig's lemma to get a path to begin with, but we don't have the hypotheses for Koenig's lemma. And we don't want to add the hypotheses for Koenig's lemma because they're not needed for the main theorem of the paper. I've realized that what I should do instead is revise the lemma. I should say, for any S subset G, if S is competition trivial, then S is totally trivial, or S is mostly trivial. Proof. Assume S is competition trivial. If S is totally trivial, we are done. Well, let's see. If S if S is totally trivial, we are done. Assume not. then S has some directed path, some infinite directed path P. Now, if S backslash P had an infinite directed path Q, then we could call the members of P heroes and call the members of Q villains, and this would contradict the competition triviality of S. So S does not have any, so S backslash P does not have any infinite directed path, thus S is mostly trivial. QED. Very happy with that. Alright, let's compile. Main result. In view of lemma 4, we are primarily interested in infinite S subset G. Actually, I might even remove that whole remark because of this new triviality development. The main technical result of this paper is a theorem which says that if infinite S subset G satisfies the convexity axiom and the IAP axiom, and if S is not too trivial, then S locally satisfies the Knight-Darwin law. What do we mean by not too trivial? We mean not competition trivial, which we define in the following definition. Because this definition is rather complicated, it might not at first glance look like a triviality condition, but we will argue below that this condition is strictly more limiting I'm sure it is strict, but there's no need to show it's strict, so I'll delete that word. We'll argue that this condition is more limiting, and hence the sense which satisfy are more trivial than the conjunction of two more straightforward conditions, each of which is manifestly one of trivialness. We mean not competition trivial, which we define in the following definition. Because this definition is rather complicated, it might not at first glance look like a triviality condition, but we will argue below that this condition is more limiting, and hence the sets which satisfy it are more trivial than the conjunction of two more straightforward conditions, each of which is manifestly one of trivialness. Definition. If S subset G, we say S is competition non-trivial if there exists an infinite directed path v1, v2, in S whose members we think of as heroes, and an infinite directed path w2, w2, in S whose members we think of as villains, such that no member of S is both a hero and a villain. If S is not competition non-trivial, then S is competition trivial. In order to justify calling this a triviality condition, we will observe that it is more strictly limiting than we'll observe that it is more limiting than the conjunction of two conditions which we call totally trivial and mostly trivial, each of whose status as a triviality condition is, we believe, uncontroversial. In order to justify calling this a triviality condition, we will observe that it is more limiting than the conjunction of two conditions which we call totally trivial and mostly trivial, each of whose status as a triviality condition is, we believe, uncontroversial. Definition: suppose S subset G. S is totally trivial if S contains no infinite directed path. S is mostly trivial if there exists an infinite directed path P in S such that S backslash P is totally trivial. Lemma: for any S subset G, if S is competition trivial, then S is totally trivial or S is mostly trivial. Proof: assume S is competition trivial. If S is totally trivial, we are done. Assume not, then S has some infinite directed path P. If S backslash P had an infinite directed path Q, then we could call the members of P heroes and call the members of Q villains, and this would contradict the competition triviality of S. So S backslash P does not have any infinite directed path, thus S is mostly trivial. We now state a weak version of the main technical theorem of the paper, whose proof is significantly simpler. We do this because we feel the easier, weaker result makes it clear what is happening. After the easier, weaker result, we will proceed to the full result, which is stronger but has a more complicated proof. The proposition is not shown. I think I need to declare that here at the top. I need to declare the proposition environment. Proposition to be strengthened in theorem 9 below. Let S subset G and assume S satisfies the convexity axiom, S satisfies the IAP axiom, and S is not mostly trivial. Then S locally satisfies the Knight-Darwin law. Right. Proof: assume that hypotheses. Assume big P equals U1, U2, dot 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 is an arbitrary infinite directed path in S. We must show that some UI has multiple parents in S. Since S is not mostly trivial, S backslash P is not totally trivial, thus there exists an infinite directed path Q equals V1, V2, dot 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 in S backslash P. Since by the assumption at the beginning of section 3, UI has less than infinity many ancestors, there must be some I such that VI is not an ancestor of UI. Since VI has infinitely many descendants in S, namely VI plus 1, VI plus 2, dot dot dot, the IAP axiom guarantees S contains less than infinity many non-descendants of VI. Thus there's some j bigger than 1 such that uj is a descendant of VI. This means there is a finite directed path x1 dot 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 xn with x1 equals VI and xn equals uj. Since S satisfies the convexity axiom, each xi in S. Let k be minimal such that there exists some L such that xk equals ul. There exists some such k since xn equals uj. Note L bigger than 1, because otherwise VI would be an ancestor of U1, contrary to the choice of I. Also k bigger than 1 since x1 equals VI is not in big P. Thus, Thus, UL has two parents, UL minus 1 and XK minus 1, which must be distinct because UL minus 1 is in big P and XK minus 1 is not in P by minimality of K. Theorem. Let us substitute. Yeah, now. Yeah, do we just directly proceed to the main theorem? I think we do. Yeah, well, let's commit, git commit, continue work on triviality. The following theorem strengthens proposition. Let's call this the preview proposition because it's like a preview of the main theorem. The following theorem strengthens the proposition preview prop at the price of being more difficult to prove. Theorem. Let S subset G and assume S satisfies the convexity axiom, S satisfies the IAP axiom, S is not competition trivial. Then S locally satisfies the Knight-Darwin law. Let's give a name to the definition of competition trivial. Label that as competition trivial definition. That big V equals V1, V2, dot dot dot, and big W equals W1, W2, dot dot dot. B2 infinite directed paths in S as in definition law. So VI not equal to WJ while IJ. Case 1. All but finitely many vertices in V are in U. I think this does not need a changing. Yeah, I think this proof should be pretty much fine. Commit message, continue work on main theorem. Okay, now we have this, in case 2, we have this incredibly complicated argument, which I think needs to be rewritten using mathematical induction. So, case 2, there are infinitely many vertices in V backslash U. Assume for sake of contradiction that no member of U has multiple parents. For each I, let f of I bigger than 1 be minimal such that U sub f of I is the descendant of V sub I. Some such f of I exists because S satisfies the identical ancestor point axiom. Vi has infinitely many descendants in S. And U2, U3, dot 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 is an infinite subset of S. For each I, since vi is an ancestor of u sub f of I, there is a finite directed path xi1 dot 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 xi sub n of I with xi1 equals vi and xi sub n of I equals u sub f of I. Since S satisfies the convexity axiom, it follows that each xij is in S. So yeah, I have to figure out where do we start the induction? What is the claim? Now ui has only finitely many ancestors, so there's some I0 in the naturals, such that for all I bigger than I0, vi is neither ui nor an ancestor of ui. At I bigger than I0. Since vi is not an ancestor of u1, f of I is bigger than 1. I think that there is like part of the induction hypothesis or something. Claim 1. J equals ny minus 1. Claim 1. For all j, that's already got a n of I minus 1. Should be less or less than negative. Not sure. All 1 less than or equal to j less than or equal to n of I minus 1. F of I is bigger than j. And f of I u sub f of I minus j equals xi sub n of I minus j. If j is equal to n of I minus 1, then that becomes xi1. I think that is what we want. I think so. We prove M1 by induction on J. For the base case, let's put this in parentheses, base case. Since Vi is not an ancestor of U1, f of I bigger than 1. Since u sub f of I has observe u sub f of I has two parents in S. U sub f of I minus 1 and xi sub n of I minus 1. By assumption, no member of big U has multiple parents. Thus, u sub f of I minus 1 equals xi sub n of I minus 1. This proves the base case. Now for the inductive case. Assume that f of I bigger than inductive case j bigger than 1. Assume that f of I bigger than j minus 1 and u sub f of I minus j minus 1 equals xi sub n of I minus j minus 1. The fact that n of I bigger than So what did we say before? We said, now n of I may or may not be bigger than 2. If n of I bigger than 2, we may continue to proceed as we have already done, blah, blah, blah. Oh, right. Right, the induction goes up to n of I minus 1. Right, so since the induction only proceeds since they are only since claim 1 is only a claim about j less than or equal to n of I minus 1, we may assume that n of I is bigger than j. Since claim 1 is only a claim about 1 less than or equal to j less than or equal to n of I minus 1, we may assume n of I bigger than j. If n of I bigger than 2, which becomes j, we may continue the process we have already started as follows. The fact that n of I bigger than j means that u sub f of I minus 1 which we have assumed equals, this would be f of I minus j minus 1 which I have assumed equals x I sub n of I minus j minus 1. The fact that n of I bigger than j means that u sub f of I minus j minus 1, which we have assumed equals xi sub n of I minus j minus 1. I'm just copying and adapting. Has two parents. I don't really understand what I'm writing. I'm just copying from my earlier non-induction argument. Has two parents in S, namely u sub f of I minus j minus 1 minus 1 and xi sub n of I minus j minus 1 quantity minus 1. Which we can rewrite, so we can say i.e. u sub f of I minus j and xi sub n of I minus j. I think we're on the right track. It does simplify nicely, at least. By assumption, no member of U has multiple parents. Thus, u sub f of I minus j equals x I sub n of I minus j. Yeah, that's the second part of the claim that we seek. All that remains is the first part of the claim, which is f of I bigger than j. We have f of I bigger than j minus 1. Assume f of I bigger than j minus 1 and u sub f of I minus j minus 1 equals xi n of I minus j minus 1. Since claim 1 is only a claim about 1 less than or equal to j less than or equal to n of I minus 1, we may assume n of I bigger than j. What are we trying to show? We want to show f of I bigger than j. The fact that n of I bigger than j means that u sub f of I minus j minus 1 is f of I minus j plus 1 has two parents, namely f By assumption, no member of U has multiple parents, thus U sub f of I minus j equals xi sub n of I minus j. Which is what we were wanting to prove, at least it's one part of it. We still need f of I bigger than j. Where did we use the fact that f of I bigger than j minus 1? F of I is bigger than j minus 1, so at smallest it's equal to j. So I guess here we should say the fact that n of I bigger than n of I bigger than j and f of I bigger than j minus 1 means that u sub f of I minus j minus 1, which we have assumed equals xi sub n of I minus j minus 1, has two parallels in S, namely u sub f of I minus j minus 1 and xi sub n of I minus j minus 1, i.e. u sub f of I minus j and xi sub n of I minus j. By assumption, yeah. So before, where did I get, so what I was doing before, I said the fact that n of I bigger than 2 means that u sub f of I minus 1, which we observed above, equals xi sub n of I minus 1, has two parents in S, namely u f of I minus 2 and xi sub n of I minus 2. By assumption, no member of U has multiple parents, thus u f of I minus 2 equals xi sub n of I minus 2. It would then follow that f of I bigger than 3. Yeah, this is why. Why does that follow? Because if not, then f of I equals 3, because f of I. Let's just copy this word for word. It now follows that f of I bigger than j, because if not, then f of I equals j, because f of I is bigger than j minus 1. Whereby you would have it now follows that f of I bigger than j, because if not, then f of I equals j, because f of I bigger than j minus 1, whereby we would have u sub f of I minus j u sub f of I minus j minus 1 equals u sub 1 but u sub f of I minus j minus 1 equals xi sub n of I minus j minus 1. Thus, u sub 1 equals xi sub n of I minus j minus 1. But xi sub n of I, but xi sub 1 equals I is either xi sub n of I minus j minus 1 or an ancestor of xi sub n of I minus j minus 1. Because xi1 is the start of a path which contains xi sub n of I minus j minus 1. i.e. the I is either u1 or an ancestor of u1 contradicting the definition of, well, contradicting the choice of I, right? We chose let's see, where do we talk about I0 first? There's some I0 such that for all I bigger than I0, if I is neither u1 nor an ancestor of u1, that I bigger than I0. Yeah, so by choice of I. Well, by definition of I0, I suppose. Contradicting the choice of I and definition of I0. This proves the inductive case. In particular, when j equals n of I minus 1, M1 says u sub f of I minus n of I minus 1 equals xi sub n of I minus n of I minus 1. Is that true? Plug in j equals n of I minus 1. U sub f of I minus n of I minus 1 equals xi sub n of I minus n of I minus 1. i.e. u sub f of I minus n of I minus 1 equals xi1. But xi1 equals vi. And u sub f of I minus f n of I minus 1 is in u, in big U. So vi is in big U, but arbitrariness of I bigger than I0, we see that vi is in big U for all I bigger than I0. This contradicts the definition of case 2. Yeah, don't even need this last line. Let's compile it and proofread it. The following theorem strengthens proposition 8 of the precedent being more difficult to prove. Theorem, let S subset G and assume S satisfies the convexity axiom, S satisfies the IAP axiom, S is not competition trivial. Then S locally satisfies the Knight-Darwin law. Proof. Suppose big U equals U1, U2, dot, dot, dot is an infinite directed path in S, we must show some UI has multiple parents. Let big V equals V1, V2, dot, 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 and big W equals W1, W2, dot, 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 be two infinite directed paths in S as in definition 5, so Vi not equal to Wj for all Ij. Case 1. All but finitely many vertices in big V are in big U. By discarding some initial segments from big V if necessary, we may assume all vertices in big V are in big U. By discarding some initial segments of big U if necessary, we may assume U1 equals V1. Typo. ASUME should be ASSUME. I should do a commit real quick. Git commit. Use induction. Case 1. All but finitely many vertices in big V are in big U. By discarding some initial segment from big V if necessary, we may assume all vertices in big V are in big U. By discarding some initial segments of big U if necessary, we may assume U1 equals V1. Subcase 1.1. There are some i's such that UI not equal to Vi. We may take such an I as small as possible. Since all vertices in big V are in big U, it follows that Vi equals Uj for some j bigger than I. Wait, what? There is some I such that UI not equal to Vi. We take I as small as possible. Since all vertices in big V are in big U, it follows Vi equals Uj. Oh, Vi equals Uj for some j bigger than I. Yeah, it can't be less than I. Yeah. Now Vi equals Uj has two parents Vi minus 1 and Uj minus 1, which are distinct since Vi minus 1 equals Ui minus 1 by minimality of I, and Ui minus 1 not equal to Uj minus 1 since j bigger than I. Subcase 1.2. For all I, Ui equals Vi, so big U equals big V. The definition of infinite biosphere implies that no vertex has infinitely many ancestors. Infinite biosphere. We're not using that terminology here. Rather, by the assumption a top section prelim section U1 has less than infinity many ancestors. Thus, there is some I such that Wi is not an ancestor of U1. Subcase 1.2. For all I, Ui equals Vi, so big U equals big V. By the assumption of top section 3, U1 has less than infinity many ancestors. Thus there's some I such that wi is not an ancestor of u1. Since wi has infinitely many descendants in S, namely wi plus 1, wi plus 2, dot dot dot, and since u sub z S is also infinite, the IAP axiom ensures wi has some descendant uj in u. We may take j as small as possible. By choice of I, it follows that j bigger than 1. Since wi is an ancestor of uj, there is a finite directed path x1 dot xn and gn bigger than 1, with x1 equals wi and xn equals uj. Now uj has two parents, uj minus 1 and xn minus 1. I wonder if we can just, because we're doing exactly the same thing as we did in the proposition here. The proposition said it's not mostly trivial. Yeah. Yeah, subcase 1.2. We'll just totally replace it by, no, wait, what? Subcase 1.2. And that'll allow us to get rid of the subcases. Proceed as in the proof of proposition ref. Preview prop. Nice. Case 2 is the really interesting case. Case 2, there are infinitely many vertices in big V backslash big U. Assume for sake of contradiction that no member of big U has multiple parents. For each I, that f of I bigger than 1 be minimal such that u sub f of I is a descendant of v I. Some such f of I exists because S satisfies the identical ancestor point axiom. Vi has infinitely many descendants in S, and u2, u3, dot 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 is an infinite subset of S. For each I, since Vi is an ancestor of u sub f of I, there is a finite directed path xi1 dot 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 xi sub n of I, with xi1 equals Vi and xi sub n of I equals u sub f of I. Since S satisfies the convexity axiom, it follows that each xij is in S. Now u1 has only finitely many ancestors, so there is some I0 in the naturals such that for all I bigger than I0, Vi is neither u1 nor an ancestor of u1, that I bigger than I0. Claim for all 1 less than or equal to j less than or equal to n of I minus 1, f of I bigger than f of I bigger than j, and u sub f of I minus j equals xi sub n of I minus j. We also need n of I bigger than j in order for that second claim to make sense. Oh, but yeah, n of I is definitely bigger than j because j is less than or equal to n of I minus 1. Claim. Claim 1. For all 1 less than or equal to j less than or equal to n of I minus j 1, f of I bigger than j and u sub f of I minus j equals xi sub n of I minus j. We prove claim 1 by induction on j. Base case j equals 1. Since vi is not an ancestor of u1, f of I is bigger than 1. Observe u sub f of I has two parents in S, u sub f of I minus 1 and xi sub n of I minus 1. By assumption, no member of big U has multiple parents, thus u sub f of I minus 1 equals xi sub n of I minus 1. This proves the base case. Inductive case j bigger than 1. Assume f of I bigger than j minus 1, and u sub f of I minus j minus 1 equals xi sub n of I minus j minus 1. Since claim 1 is only a claim about 1 less than or equal to j less than or equal to n of I minus 1, we may assume n of I bigger than j. The fact that n of I bigger than j and f of I bigger than j minus 1 means that u sub f of I minus j minus 1, which we have assumed equals xi sub n of I minus j minus 1, has two parents in S, namely u sub f of I minus j minus 1 minus 1 and xi sub n of I minus j minus 1 minus 1, i.e. u sub f of I minus j and xi sub n of I minus j. By assumption, no member of U has multiple parents, thus u sub f of I minus j equals xi sub n of I minus j. Let's elaborate slightly more. Put in parentheses here, one of the two facts we were required to prove. It now follows that f of I bigger than j, the other fact we are required to prove. Because if not, by assumption, no member of U has multiple parents, thus u sub f of I minus j equals xi sub n of I minus j, one of the two facts we were required to prove. And now follows that f of I bigger than j, the other fact we are required to prove. Because if not, then f of I equals j, because f of I bigger than j minus 1. Whereby we would have u sub f of I minus j minus 1 equals u sub 1. Why is that u sub 1? F of I equals j, so u sub f of I minus f of I minus 1. Oh, it is indeed equal to u sub 1. But u sub f of I minus j minus 1 equals xi sub n of I minus j minus 1. Thus, u1 equals xi sub n of I minus j minus 1. But xi1 equals vi is either xi sub n of I minus j minus 1 or an ancestor of xi sub n of I minus j minus 1, because xi1 is the start of a path which contains xi sub n of I minus j minus 1. Change these brackets into parentheses. Because xi1 is the start of a path which contains x. I sub n of I minus j minus 1. i.e. vi is either u1 or an ancestor of u1, contradicting the choice of I in definition of I0. This proves the inductive case. In particular, when j equals n of I minus 1, claim 1 says u sub f of I minus n of I minus 1 equals xi sub n of I minus n of I minus 1, i.e. u sub f of I minus n of I minus 1 equals xi1. Get rid of some dangling white space. In particular, when j equals n of I minus 1, claim 1 says u sub f of I minus n of I minus 1 equals xi sub n of I minus n of I minus 1, i.e. u sub f of I minus n of I minus 1 equals xi1. But xi1 equals vi, and u sub f of I minus n of I minus 1 is ambigu, so vi is ambigu. By arbitrariness of I bigger than I0, we see that vi is ambigu for all I bigger than I0. This contradicts the definition of case 2. What was case 2 exactly? Yep. Nice. Conversion to mathematical induction complete. Commit message, finish conversion to mathematical induction. And I'm going to stop there for today. I'm Dr. Samuel Allen Alexander. Please like, comment, and subscribe. I'll see you in the next video.